that we looked at yesterday and together with the reaction forces. So that is the first thing that we need to do. Of course, if you are asked to draw the shear force diagram, bending moment diagram, you, as mentioned yesterday for the beam problems, you can just determine one side, either these reaction forces, then by using the appropriate free body diagram, after you cut, you can draw the whole axial force diagram, shear force diagram, and bending moment diagram. Either you get these reaction forces or this group of reaction forces, then either side you can start. But that means you do not have to calculate all. Okay? So if you are not asked to calculate reaction forces, then you can just get one side and you can already start with the calculation of axial force, shear force, and bending moment. Okay. Now, in order to, before we go in detail, the process of getting the shear force, bending moment, and axial force, the first thing that you need to recall is the definition of shear force, bending moment, and axial force, which is, how is it defined? Yeah? Who is raising hand? Rafika, you have questions, I think. You have, you say hello, you want to say hello, or you have a question? Disappear now? Okay. Any question, class? I cannot hear suddenly. The mic is mute or yesterday. Then please type in the chat again. Okay. Because if you say something on the mic, I cannot hear you because I have plugged in the mic using this. I can't hear you. So now this is the first thing that I mentioned is in order to be able to get the shear force diagram, bending moment diagram, and if axial force diagram is also needed, the steps that you have to go through will be similar to the case for beam. If you're using the section method, then you need to know how many cuts, how many times of cutting you have to do. So for this particular example, how many cuts we need? How many times of cutting you need to do and then get the shear force and bending moment? How many? You have to cut at least once here, and another one at least once here, and another one is here. So there will be three cutting. So in general, this is the first thing that you have to know. For each of the member, at least you need to cut once, at least once. And if the loading changes, then you have to cut more. So here, the loading is all the way the same, so you have to cut once. Loading all the way the same, have to cut once. So this another member, of course, although it's no loading, you have to cut. So if there is a loading somewhere here in the middle, so this have to cut twice, one before and one after. And if there is a loading somewhere here, then of course I have to cut here and here. If the loading changes along that member from one side to the other, you have to cut. Here, although there is no loading because you will get axial force. Okay, bending moment and shear force 0, but you get axial force. So here also you need to cut. So at least cut once on each of the member for frame. Then along the frame, if the loading changes, then you have to cut before the loading changes. So that is the first thing that you have to be aware of. So the cut is as we look at the problem with the beam, the cut is it's not necessary before a hinge. After the hinge, you have to cut. So the hinge is so happen at the joint here. If the hinge is somewhere here, along this member and the loading is all weighted the same, you don't have to cut before the hinge, after the hinge. So along that member, you need to cut only once. So that is the first thing that you need to do. Then after cutting, then you need to know how the shear force, bending moment, and axial force are defined. So when you cut here, so the frame will be separated into two. When you cut along here, the frame is separate into two parts like this. So you can calculate the shear force, axial force, bending moment at this cut section for this particular member by using this free body diagram or using this free body diagram. Either one, it can be used. Suddenly you don't see me, okay? You don't see me here now. Okay. Can you see the drawing class was online? Yes. Can you see this drawing? Anyone? Yes. 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 Yeah, you can see, yes, but over there, yes or no? Yes, okay. Only you can't see me, okay. So here, the same thing. If you cut here, then you either use this one or this one. Okay. Then if you cut here, then you get the frame is cut into two. So you use either this free body diagram or this free body diagram for the second cut. And lastly, for the third one, when you cut through here, then you're going to get the frame cut into two parts. So you use either this free body diagram or this free body diagram. So important nice thing is when you cut here, or when you cut here, when you cut there, when you draw the free body diagram, how will be the positive directions of axial force, shear force, and bending moment is being defined. Those are the things that you need to be clear. Okay, so those parts, I think, in the notes, because if you use this side or that side, the positive directions will become different. The positive directions that we use to represent axial force, shear force, and bending moment will depend on which side you are using as the free body diagram for getting the internal force. Okay. So this is for this here, and for here, if we cut here, okay, then you get the whole thing like this. This is for this member. You cut here means you want to get the axial force, shear force, and bending moment equation for this member. So it is define axial force, shear force, bending moment, axial force, shear force, bending moment. These positive directions have to be clear how it is being defined. Okay. Then here, if you cut for this member, if you cut there over the sections, then if you use this free body diagram, then this is similar to beam, beam horizontal. So this is a positive directions, shear force, axial force, bending moment. So that is the things that you must be familiar with after you know how many cuts you need to do. Okay. So you can, if you cut here, you can use this free body diagram with this. If you calculate the AY and if you calculate the AX, if you know the AY, you know the AX, then you can use this to calculate axial force, shear force, bending moment. If you do not calculate this, in your reaction forces, you only calculate this. You only calculate dy. You can also calculate the shear force bending moment on this part, but you have to use the free body diagram of this part. You have to use the free body diagram of this part. If you do not calculate the reaction forces AY, AX, because you just need the reaction forces dy, you can already calculate all the axial force, shear force, bending moment, axial force, shear force, bending moment, and axial force, shear force, bending moment. But the calculation will be a bit more lengthy. Okay. But if you have calculate AY, AX, then depending on the free body, depending on which sections, then we can choose the free body diagram, which is easier to consider. So for this section here, it will be easy to use this free body diagram. For this cut section here, it will be easy to use this free body diagram because this is equal to negative of this 0, this 0. So it will be easy to choose the free body diagram, which is involving less number of forces to calculate the axial force, shear force, and bending moment. So that is how the first few things that you need to be aware of. Okay. Now, next I'm going to show you, for example, if I know AY and AX, then I'm going to calculate the shear force, bending moment, and axial force here. Then because axial force, shear force, and bending moment, axial force and bending moment, axial force and shear force is always defined following the member. Following the member here. The direction is like this. Okay. The direction of axial force is like this. Okay. Follow the members. But your reaction forces is like this. One is like this. Okay. The other one is like this. So when we want to consider the axial force, then we need to consider this component in these directions, also this component in this direction of the axial force. So that is the things that you must be aware of and how to get this component of this in this direction, component of this in this direction. The same thing for shear. Your shear is like this. But your reaction forces we calculate following the y and x. So when we want to calculate the shear force here, you need to know the component of this in this direction, the component of this in this direction. So those are the things that we need to be aware of. Okay. But when we come to this part here, because the shear force is like this, okay, then we can consider directly the direction of this in y direction in the calculation of this. If you use this as the free body diagram to calculate shear force, because this shear force now on this member for this cut section is now in vertical, so it's easy. So this one does not cause any shear force. This one does not contribute to shear force. Only this one contribute to shear force, plus, of course, the applied loading here. When we want to get the axial force for this section, you use this free body diagram. So this is axial force direction. So this will affect the axial force. This one will not affect the axial force. And this loading, that's why yesterday, please read the question. This loading is in which directions? If this loading is in vertical, then it will not affect the axial force here because this loading is in vertical. Okay. So these are the few things that you must be aware of, okay, especially when we want to get axial force, shear force in member which is inclined. Okay. Now, how to get the component of this in this direction, the component of this in these directions? You need to make use of this inclination here, the theta here, the theta here. Okay. So that theta has to be calculated from the dimensions of the problem given to us, the theta. Okay. And what we need is actually cosine theta and sine theta. So we don't need this theta. What we need later in the calculation when we go in more detail will be the cosine of this angle and sine of that angle to get the component. So how to get the component of this in this direction when we want to calculate axial force, the component of this in this direction when we want to calculate the axial force, you must be familiar with that. If not, then it's going to take you a long time and then you might make mistake. And of course, it will cause the wrong shear force diagram, the wrong axial force diagram. So this one, let me just share a little bit on this. Okay. These are some of the basic things that we need to be aware of. So okay. So now this theta, if we use this as theta, then if we have this AX, okay, then in order to get component in these directions for the axial force, okay, so what you need is you need to get for this, you need to get this component. Okay? Need to get that component. So how to get that component? You need to relate to this angle. Okay? If this angle is theta, if the angle is theta, this should be theta, and this should be theta. So that relationship, you must be able to identify it clear. This and this opposite angle, it will be the same. This plus this is 90 degrees, this plus this 90 degrees, so this must also be theta. Okay. So with that, you must get it fast. Huh? Okay. So if this is theta and this particular blue one will become AY sine theta. Okay. So this AY sine theta will contribute to axial force. So axial force, when we calculate axial force, it will be equal to minus AY sine theta. Then this one, next is to get the component of this in this direction. So that component will be this one, okay? Or that component will be, it's a bit congested. This it will be this angle, okay? This component of this in this direction will be this. or is this one here, okay, this AX. Component of this in this direction will be this component. And because it is very congested, I can also draw it here. This is a component. Okay. So this component is, this blue one is the component of AX, which is horizontal one in the direction of axial force direction N. And this one, if this is theta, so this one become, this is AX cos theta. Okay. And the direction is like this. So if I now want to consider this in the calculation of axial force, it becomes minus AX cos theta. So these are the calculations that we need to be aware of, especially when we want to get the axial force. Then, of course, the other things will come from this vertical force, the vertical distributed load acting on this. We need to find the component of this in that direction. We need to find the component of this in this direction. So that is I start with this reaction force first. Okay, and how to find this? How to find this here? So let me draw another figure. Okay. So I have shown you how to get the component of AY, the reaction force component of AX in the direction of the axial force. Okay. So now how to get the component of the distributed load, which is the vertical one. What you need to do is, because this is vertical and our axial force is in this direction, so you need to look at this vertical load, which is acting on the member. And this is angle theta. You need to get the component of this. You need to get this component. Okay. You need to get that component. This is 20. So what is this? And that is the one that will affect the axial force. This is distributed load 20 kilonewton per meter, but it is in this direction, but the axial force in that direction. So you need to get the component of this, which is in the same direction of the axial force. Okay. So how to get that? Then you need to go back to the basic here now. Okay. If this is theta, then this becomes theta, right? Then this plus this is 90 degrees, so this is theta, right? So that relationship of the inclinations, I think you must get it. You must get it fast. And as I mentioned earlier, what is important is not the theta itself, but the sine and cosine, because what we need is sine and cosine. Okay. So this one become, this is 20. So the red one is 20 sine theta. Okay. So to get the axial force, and this is acting like this, so it becomes plus 20 sine theta multiplied with x. So this is the thing that I would like all of you to be aware of, especially when you have inclined member. Inclined member. First, what is the definition of axial force, shear force, the directions, which always follow the member? If it is inclined, then it follows axial force, shear force perpendicular, and bending moment you have to. Bending moment is either clockwise or counterclockwise, depending on which side you are using. Then, when we want to get this end of this member, then you need to, all the forces here must be converted into the component in that directions. Okay. So this has to be converted, get the component in this direction. This must get the component in this directions, which is this, and for this, which is this, and for this, which is here. Okay. So there's no other forces. There's no other forces, which is we need to consider. So that will give us the axial force for this member. So the axial force here will become N equal to AY is minus 160.58. Sine theta, you can find sine theta. Sine theta, this is theta. So if I use this, so sine theta, we can find what is the sine theta here. Okay. So sine theta will be this height here, which is 7.5 divided by that length. 7.5 divided by the length, you can get sine theta. Okay. Sine theta, make use of this diagram here. If you want to get this is theta, so sine theta will be this height, 7.5 divided by this length here. You get sine theta. Then cos theta will be this length, 3.75 divided by this length, you get cos theta. So what we need is not the angle itself, but the sine and cosine. So AY is this, okay, and AX is this, 38.37, so minus 38.37 cos theta. Going to calculate the cos theta plus 20 sine theta x. X is the coordinate that we use to represent where is the cut section along this member. So X is always follow the member. X is not vertical, not horizontal, always follow the member. Follow the member in that direction. Okay. So if we calculate this, what is this? I think, and anyone calculates, okay. What is that value there? Sine theta is, sine theta, you get 3.75 plus 8.38. Sine theta is 7.5 divided by 8.39. Right. 3.75 divided by 8.85. So you compare whether your calculator and my calculator, because it is same. Did you get the same answer? This one also you need to know how to calculate. If you this will take time also to calculate this sin theta and cos theta. 8.385 is the length of this. Okay? Anyone get different answer? Okay. Okay. So now if you have, because I want to get this, so that when we want to draw shear force diagram, bending moment diagram, I get this equation n here. So n will become, now you minus 160.58 multiplied with 0.894 minus 38.3. 447. 0.71. 1. 17.88. Any questions so far? Can you follow those online? Can you see clearly? Suddenly I write outside. Suddenly I write here. Right? You cannot see. Please, please let me know by chat. Yeah. Okay. So now we can do the same thing for shear force. For shear force. Okay. Let me write down this. You need sin theta is, what is the value? 0.894 cos theta. Okay. Now, class, if the inclination of this member can also be represented by this angle, yeah? It depends on what angle you want to use. If you use the angle alpha, then of course, then the calculation will be, the sine maybe become cos, cos maybe become sine, but the answer will be the same. Okay. So this angle depends on which angle you are using. Okay. The angle can be measured from horizontal to this, or from this to here. If the angle is given to you, then you use the angle directly. If not, then you have to calculate from the dimension given. Okay. So I use here the angle theta from here, so that is the calculations. Okay. Any questions? Okay. Now we go to shear. Okay. So I have advantage. I just delete this. You don't have advantage, okay, because you have to use your liquid paper, or you have to draw again. Okay. So pay attention first. I will record this and you take down the main point. So shear now for here is defined like this. This is shear. Okay. So now if you define like this shear, so everything that we need to consider the force must be resolved in that direction now. So this one will become, so I will take away everything of this. Okay. Okay. Same thing here. Here I take away this now because I want to calculate shear force now. So the shear force B so if we try to calculate now, so the shear force become need to record down this, okay, so that I n equal to 0. X, yeah. So shear force is S equal to, now you need to get the component of this in this direction now. The component of this in this direction, which is parallel to the shear force direction of that member, and the component of this in this direction now. So everything has to find in that component. So the component of that will become, this is the component. So that become AY cos theta. So we have the direction is like this, the shear force is like that. So this is AY cos theta. And the next one will be AX get in that directions. Okay. So it will be this component. Okay. This, try to get it in this component. This is parallel to that. So this is the component, and that one will be AX. This is theta, AX sine theta. And the direction is like that. The direction is like that. Follow this. So if you bring to the other side, it become minus. And this, which is coming from here, we need this shear force now. So we need to get the component of this 20 kilonewton per meter in this direction. So this one will be 20. This is theta, this theta, this is theta. So 20 cos theta. And the direction is like this, same direction as the positive shear force. So minus 20 cos theta. This is in kilonewton per meter multiplied with x. So if I substitute here ay again, value of ay, value of cos theta, value of sine theta, then we can simplify that to become, that's why ay, okay, 16058 multiplied with four, 7.48. Minus 20 multiplied 1.47. Oh. Okay. So this is the shear force is changing with x. It should be changing with x because you have a UDL here in vertical direction. the axial force also changing with x. So this is how we get the shear force for this cut. Okay, we are still with this cut. Yeah, we still have this and this to do, but this is the most difficult one because of the incline. Okay. So any questions clear for this? Okay. So let me write it down here. The n as the n. Okay, I want to put it here. Okay. So the shear force is 37.488.94x for this part of the frame. That is the variation of axial force and shear force. Okay. It is recorded. After that, you can get back again, just write down the main point. Okay. So now, bending moment. Okay. So it's a lot of jobs. Yeah. Bending moment. So make sure your calculator have enough battery. Make sure that you have enough pen. Bring enough pen, pencil, or eraser. Okay. Liquid paper. Okay. Sometimes we have students forget to bring calculator. So we are in trouble because if you don't use calculator, then yes. So don't forget to bring calculator. So next, we want to get the bending moment now. So bending moment, we need to, when I show you the process for bending moment, the important thing is remember the definition of bending moment is force multiplied with perpendicular distance. So the way we calculate bending moment will depends on how easy we get the perpendicular distance. It must be force multiplied with perpendicular distance. So we now change to bending moment. So bending moment is for this. If we take cut here, we take this part. This is the positive bending moment direction. Okay. So for here, the bending moment will be like this. So now I want you to remember your x is follow this. Okay. The x, you must follow the member. The x is the coordinate to represent where is your cut section along that member. Must always follow your member. The x is not like this, it's not like that, it's like this for this member. For this member, of course, x is like this. For this member, x is like that. If you start your origin from here, if you start your origin from there. The important thing is x, when you want to calculate axial force, shear force, bending moment, it follow the member. Take note of that. And now we are going to calculate the bending moment. Bending moment caused by all these forces and all the distributed load at this section now. Okay. So what we should do is these are all theta, the same. Now I emphasize again, bending moment is force multiplied with perpendicular distance. Okay. So now we want to get the bending moment at this section caused by this AY. Next bending moment at this section caused by AX. Next bending moment at this section caused by this distributed load. And remember, bending moment force multiplied with perpendicular distance. So remember that, then M. So for this is M, and for this moment caused by AY to this section will be opposite, will be against this direction, negative to that direction. So if we bring to the other side, it becomes positive. So we have AY multiplied with AY. Okay. So AY, so I can draw this for you. AY, the direction is like this. Can you see it? How small you can see like this? You can see it. Okay. This is the limit. Can see. I think it's a pity those online maybe cannot see. Can you see this? Can?
Cannot, doctor.
No response. Maybe draw a bit bigger here. Okay. AY is here. Okay. And we want to take moment at this point here. So you can multiply with the perpendicular distance. The perpendicular distance is you draw one line which is parallel to the force, and this is the perpendicular distance. That is your perpendicular distance. Okay. And remember, this is X. This is X. X. Okay. Perpendicular distance is this, and this is theta. The angle is theta. So this perpendicular distance will be X cos theta. This perpendicular distance that you need to multiply with this AY to get the bending moment caused by AY at this section here will be this AY multiplied with this perpendicular distance, and this perpendicular distance, if you consider this triangle, if this is X, this is theta, X cos theta give you this distance. Okay. So AY multiplied with X cos theta give us the moment caused by this at this section here. Okay. The other way that you can do is you find the component of this in these directions. Yeah, you get the component of this in these directions. Then you directly multiply with X. You get the bending moment caused by this at these sections. Get the component of this in this direction and get the component of this in this direction. The component of this in this direction will not cause moment. Only the component, this component will cause moment here. And that component is AY cos theta. AY cos theta. Then you multiply with perpendicular distance is X. So at the end, they are the same. But the most important thing is here, back to the basic, moment must be force multiplied with perpendicular distance. So you keep that in mind because in the exam you must apply that fast. Okay. So next one, find AX now. So AX in a similar way, AX, again, AX is this direction, AX. You want to find moment here. So the perpendicular distance is, you have to draw a line parallel to this. Okay. So this is the perpendicular distance to be multiplied with AX. And this AX causing moment in the same direction as bending moment M. If we moment will be the same direction as this. You move to the other side, it become negative. AX multiplied with the perpendicular distance. This is X. This is theta. So it becomes X sine theta. Okay. So next we come to this here. Moment caused by this distributed load in vertical direction along this inclined member at this section M. So what we can do is you can get first, there's two ways to do that. Get the component of this. Yeah, get the component of this. This component. And then you get this component first, and then you make it the equivalent load of that component. Then you multiply the perpendicular distance, which is you multiply with this distance. Then you get the moment caused by this. So this one just now is equal to, this is equal to 20 cos theta. Okay. 20 cos theta in kilonewton per meter. This is in kilonewton per meter. Okay. So we know that for distributed load, you can convert that to equivalent force first, acting along this length. So you have to multiply with X. So this blue one is the total caused by this, acting along this length of X. So the blue one become 20 cos theta multiplied with X. Okay. 20 cos theta multiplied with X. Then this moment, this one will be X over 2. So the moment caused by this distributed load at this section, and the direction of the moment is the same as this. So it becomes, when we move to the other side, it becomes negative. This is the blue one, 20 cos theta X multiplied with X over 2. Okay. So finally we get, okay. So what do we get here? Okay. You can simplify this, AY cos theta minus AX cos theta. So AY is 160.58. That's 47. 38.37 multiplied with 0.894, 37.48. Yeah. This one I already simplified this. What is cos theta, sin theta? What is AY, AX? Substitute there, and XX here, so it come up with an X. This one will be 10 cos theta X squared. For 7. So class, that is how we consider bending moment caused by all the forces acting on this free body diagram, this side here, on this section here. So we get n, we get s in terms of x and x, but bending moment, because there is distributed load, so there is an x squared. There's an x squared here. Okay. So bending moment, there are two ways that you can get the bending moment equation. It will be at the end the same. It depends on how you want to calculate how easy to get the perpendicular distance. How easy to get the perpendicular distance. And remember, moment must be force multiplied with perpendicular distance. Force multiplied with perpendicular distance. Sometimes it's easy to consider force in horizontal, vertical, and in order to get it to calculate a perpendicular easier. And sometimes it is easier to consider like this and then to get the perpendicular distance directly in this way. Okay. So keep in mind, class, moment, force multiplied with perpendicular distance. So then you can get the bending moment for this member, which is this minus this, and it is squared. So it is a curve now. It should be a curve because you have distributed load. So now, okay, I'm going to transfer this here. Okay. I have to erase this, okay, class. This one, I'm going to bring it there. Okay. So that is how we get, this is only for the first part. So I spent very long time explaining about that. But in the actual exam, you have to make it faster. Right? But you have to be clear